yesterday, we looked at models that go beyond lambda CDM, and we were interested in models that reduce the sound horizon because we had identified reducing the sound horizon as an obvious way of making progress with the Hubble tension, because reducing the sound horizon requires you to increase the Hubble parameter to keep very basic observations we have in cosmology intact. And so first of all, we looked at how to lower the sound horizon, and we said that one obvious way of doing it is to have an energy injection. And then we asked what are the effects of doing that. So the obvious effect, which I call the primary effect, is raising H0. I mean, that's what we are interested in. We want to increase the early universe prediction of H0, the CMB prediction, in order to make it compatible with the locally observed value from the distance, let us say. But then we realized quickly that when you lower the sound horizon, you also need to increase omega m, the dimensionless matter density. And that was needed because you have to fulfill two obvious constraints. You want to preserve the angular scale of BAO, but you also want to preserve the angular scale of the sound horizon in the CMB. These are not exactly, they don't have exactly the same dependence on these parameters. So these are two conditions. So one condition you can satisfy by raising H0, but you need a second dial to make it work. So you also need to increase omega m. So that's what we also did see. But then we also realized that lowering the sound horizon for very general reasons, I mean, once you have to do it with an energy injection, you are also going to change the diffusion damping in the CMB. You enhance it. And these two secondary effects, as I called them, they require some compensation to preserve the fit to the CMB. And yeah, I'm going to talk about this a little bit more today in case of omega m, but we have already seen that the enhanced diffusion damping can be partially compensated by changing the initial conditions, by changing the amplitude and spectral tilt of inflation. And that's something to keep in mind. All of these models have the property of changing what we learn about inflation. And then we moved on to a more concrete model, which gives you an energy injection. That's dark radiation. It's typically parameterized as an effective number of neutrinos, even though it might not have to do anything with neutrinos. It's just the way you normalize it. So you have some dark radiation energy density, and you measure it in units of the energy density that corresponds to one neutrino species. And in the simplest case, this is just a constant throughout because, well, both are radiation, both scale the same way with the scale factor. As we know, radiation scales like 1/8 to the power 4. So that scaling drops out and you just get a constant. But then we also looked at the case where the dark radiation changes internally. So when the number of degrees of freedom that constitute that dark radiation change due to annihilation, you could have some dark positron and dark electron, and they could annihilate. Then you change the number of degrees of freedom, and that introduces a step feature. And these type of models, I wanted to point them out because they are often used as sort of a benchmark for early universe modifications of lambda CDM. And you find them a lot in the literature. And they are still interesting because they are very minimal, but typically they have problems at fully resolving the Hubble tension because they tend to have little flexibility in getting the entire power spectrum right. But still, you can look at more complicated versions of it, and I think this is one of the the more important classes of models. Okay, so let's move on. Today I want to talk about early dark energy. So that's B3. And this is a class of model that has been studied. Well, the concept of early dark energy is actually pretty old, but in the context of the Hubble tension, this is an idea which was first discussed in 2018 by Poulin, Smith, Cavall, and Kamionkovsky. And their model, they have a very concrete scalar field model for early dark energy, and I will refer to it as ICTS-TIFR. So that's a very specific proposal for early dark energy, and it kind of kick-started this early dark energy idea as a resolution to the Hubble tension. But since it's a very concrete model, I want to postpone talking about that model until later, today or tomorrow, and first talk about a more general fluid approach, and I call it a triggered fluid approach, and that goes under the name of new early dark energy. So that is something I have been working on with my collaborator Martin Slot in Denmark, and the important aspect which makes it new is the presence of a trigger, and we are going to understand why that is relevant for us. But the idea, or the first idea, is to have a rather model-independent, or initially an entirely model-independent fluid approach, and then we look at more specific models tomorrow. But I will also summarize the original proposal, ICTS-TIFR, and there are many other models that work along this line, so relying on one scalar field. Okay, so this is the plan. So let's start with the background. So as usual, we start with the background and then we look at perturbations. So we want to introduce a new fluid into the into our cosmological model, and that fluid, as usual, is characterized by an equation of state. I mean that you are now very familiar with. And that equation of state, I call it WEDE. In this kind of general fluid approach, we describe initially as -1. And as you know, the equation of state of -1 corresponds to the cosmological constant or dark energy. But yeah. And this equation of state is the right description for the fluid at early times. But then we assume that there is a time A star, or a scale factor A star, where this fluid abruptly changes its properties. So how this fluid is going to abruptly change its properties, there I'm going to present a concrete microphysics idea tomorrow. We are going to talk about a phase transition. But in this kind of general approach, we are just going to assume that there is a fluid where the equation of state suddenly changes from -1 to something else. So I call it the equation of state of the decaying fluid. That in general can depend on the scale factor, and that happens then for later times. And we will see that the original ICTS-TIFR model effectively has a very similar behavior. Okay, So the picture is the following. You have this fluid. It has an energy density, rho EdE, over time. And it initially is a constant because the equation of state is -1. And as you know, this corresponds to a constant. And then it decays. And this happens at this time A star. Okay. And the presence of the EV scale here can also be understood because the EV scale is the energy scale of the cosmic fluid shortly before recombination. So, and we have seen yesterday, we want to change physics before recombination, but not too early. So we want to do EV scale physics. So that's why there's the EV scale. Okay, very good. And there is some crucial ingredient which applies to all these early dark energy models. You want this decay to be quick enough. So you want to have a quick dilution. So that means that this decaying fluid should be characterized by a scale factor which is at least as large as the one of radiation, but ideally even larger. So you remember that a fluid with a general equation of state, actually I'm going to write it down. So a fluid, in this case, this EdE fluid, we can describe it as some constant value at this time, and then the time evolution is given by this integral. So this is for A larger than A star. Before that point, the value is just going to be a constant denoted as rho star. And what we get is, well, I've already wrote that down, I think, in the first lecture. So it's ln A star to ln A of d ln A 3 times 1 plus W of that decaying fluid. So this is how such a fluid decays, and you see this is supposed to happen still during radiation domination. So we say that it can be happening close to equality, but typically this transition happens slightly before equality. So in order for this decay to be efficient compared to the other cosmic fluid around, we need it to decay faster than radiation, because that's the fluid, the dominant fluid component we are comparing it with. Okay, and you see, I mean, how do we get a faster decay? We need a larger equation of state. The larger W is in this expression, it comes with a minus sign. The faster it goes down. Yes. Yeah. Let me come to that. I mean, it's more like okay. I think I should become clear from this plot I wanted to do anyhow. So let's plot rho EdE over rho lambda CDM. So you compare to the fluid, the standard part of the fluid, radiation, matter, and the CC. And then you see that initially rho EdE behaves like a constant, right? But we said everything happens still during radiation domination. So you compare a constant to something that scales like radiation, like 1 over A to the 4. So you get a very steep increase. It's proportional to A to the power 4. And that's the steepest possible increase you can get without introducing phantom type matter. I mean, this gives you the sharpest energy injection you can dream of, without doing too exotic physics, let's say. But then what happens is that at this point, you start to decay. And let's assume that this decaying fluid equation of state, just for concreteness, is 2/3. So it's somewhat larger than the equation of state of radiation. Just choose this because then numbers work out nicely. And then what you find if you plug this constant value in here, you find that for 2/3, this is going to scale as 1/8 to the power 5. So you compare 8 to the 5th with 8 to the 4th from radiation. So it goes down like this, 8 to the -1. And from equality on, you compare it with the dominant matter density, and then it goes down like A -2. And finally, you compare it with a cosmological constant, and then it goes down even quicker. So what you see here, it's a very localized energy injection. Now coming back to your question, if the equation of state is a third, say, then we get a constant plateau here, and then it goes down like this, right? But if it's smaller than a third, then it's going to increase further. So that is a problem, because then we lose control over the amount of that energy injection. Then we end up with a big modification of lambda CDM. We want a small controlled modification of lambda CDM. We have a kind of sharp injection. Otherwise, we will be certain that the corresponding cosmology doesn't work. But we keep it as a free parameter anyhow. I mean, I'm already anticipating what data likes and what data doesn't like. But we can understand it from this picture that doing something too drastic is going to take us away from lambda CDM too far. Okay. Then we also introduced this parameter, which is typical in the literature. It's the fraction, the maximal fraction of this new energy component. It's simply defined as rho EDE divided by rho total at the time A star. So when at this point, when it has the maximal fraction. Okay, and then I come to a very useful simplification in these models, which applies in the cases where you have a very quick dissipation, and these are the cases which are going to be preferred by data. So actually this value of 2/3 is very close to what you get as the best fit value when you test these models against data. So as I said, in general, this is a function of scale factor, so it's non-constant. But what you can do is you can Taylor expand it. It's a little bit, this motivated one of the first exercises we did, right? And then you just write it with logs, and higher order terms. But the point is that if this leading order term is large enough, meaning you have a large enough decay, then before the second order term becomes important, your fluid relative to lambda CDM has already decreased so much that you lose sensitivity to the higher order terms. So that is something one can make use of in this kind of simplified description. But of course, you can also just look at higher order terms in this Taylor expansion, include them in your model description, and use that. But to make things simpler, I will here only consider the leading term, which then is just a constant, which simplifies the scaling, of course. Then rho EDE is just the value at the time where it starts to dissipate times A star over A to the power 3 into 1 plus WDF, where this is then a constant. So this you get when you assume, from this equation, when you assume that the W is a constant, right? Then you can pull this factor out, you can perform this integration elementary, and yeah, you get log of A, and the exponent of log then just gives you the power of A to the power of this factor, which is this. Okay. And in one of the exercises, you're going to show that a reduction of the sound horizon as needed for tracing the Hubble tension is requires something like 10 FEDE of the order of 10%. I mean, the precise number depends on where this transition happens. The earlier it happens, the more energy injection you need, which has to do with the fact that the sound horizon picks up its main value closer to recombination. So the closer to recombination you are, the less of an energy injection you need. So there's this balance. Okay, so you see it's a very simple background model, nothing extremely complicated, an equation of state going from -1 to some other value that corresponds to decay, and that gives you kind of this relatively localized energy injection. So if you compare to what we did yesterday, dark radiation comes in as a constant and then remains a constant until equality, and then it goes down like A to the power -1. So this is not localized at all in comparison. Okay. So now we have to look at perturbations. And perturbations are going to be very important. So there are two regimes. There's the A smaller A star regime, so before the transition happens. And in that case, EDE acts like a cosmological constant. And then I think, I don't remember now whether it was in the first or second lecture, we looked at perturbation theory of a cosmological constant, and we concluded that for a perfect cosmological constant, perturbations are 0. So initially, there are no perturbations in this fluid because it's just a cosmological constant. And as the name already tells you, it's perfectly constant. Okay. But after that time, A star, things are different. And then suddenly we can have perturbations because we have a fluid with a non-vanishing, I mean, with an equation of state, which is somewhat larger than a third. And we have seen the perturbation equations, these are oscillatory equations, yes? Mm-hmm. Yeah, so that's the point why it needs to be very localized. So you see, this is the amount of early dark energy versus lambda CDM, and this, let's say 0.1 when it's maximal, but then up until today, it has already decayed by many orders of magnitude. I mean, you see it scales. So in terms of redshift, here we are at redshift 4,000 or 5,000, and then we go down here with a relatively aggressive scaling. So the contribution, I mean, by today it's suppressed by maybe, so now I don't quite remember the number, but at least by 5-6 orders of magnitude compared to the lambda CDM fluid. Yeah. Yeah. Will it not change like other physics? Absolutely. This is why we did this general discussion yesterday. So it will have an impact, and it will be important to compensate the effects of of the increase in omega m and the increase in the diffusion damping. But well, in diffusion damping, we can mostly adjust via initial conditions, but omega m is going to be important because omega m, increasing omega m gives you an earlier onset of matter domination. You have more matter, so matter domination starts earlier. But having this additional fluid component delays matter domination. So you see, there are going to be compensating effects, and it's an intricate interplay. Because naively, I completely agree. If you just write down such a model and say you change the energy budget by 10% during the CMB epoch, everyone would have said, oh, that cannot work. But interestingly, it works. And now we need to try to understand why it works. And these are the mechanisms that play together. But I'm going to talk about the details. Yeah. In this one, yes. So lambda CDM comes down as so we are still in radiation domination. So it goes down like 8 to the minus 4. So it comes like this. And then, so it's here, it's kind of a 10% fraction. And then equality, it changes its scaling. It becomes a little, it goes to matter scaling. So it's more like this, or maybe not as much. And then dark radiation, it goes to a constant. Sorry, dark energy. So this would be rho lambda CDM. Okay, does that make sense? So you have 8 to the minus 4, here you have 8 to the minus 3 in matter domination, and here you are constant. Whereas this fluid just quickly decays. Yeah. A star, yeah. So that is a fit parameter. But it's you keep it free, you allow the model to do it whenever it wants to. But what you find is typically that it's between redshift 5,000, so A star would be 1 over 5,000, up to very close to equality. That's the typical window between 5 and 3,000, depending on the data sets you look at. So you typically have that energy injection around that time. And my understanding is that this happens because you want to have the freedom to delay the onset of matter radiation equality. And so you want to be close enough to equality to have an effect on that. So that's one part of it. Okay, but perturbations are important in this business. And the big question is, so perturbations are initially 0. But then in this decaying fluid, we know it satisfies an oscillator equation, and perturbations are going to be non-zero. They are also going to be gravitationally sourced. You remember there were these gravitational source terms. So how to initialize them? So what are the initial conditions at A star for our delta rho EDE? And the first thing would be to say, can we set delta rho EDE at A star to be 0? Because it's 0 before, and then, well, we have this transition, and then we expect the perturbation to be 0. But the answer is no. And the reason is, there are two reasons to give you an idea of why that's not possible. So first of all, setting it to 0 at that time is not a gauge invariant statement. So what I mean by it, if you set it to 0 in one gauge and you go to a different gauge, it will be non-zero in that gauge. Because this is not a gauge invariant variable. And so what you see, if you look at the transformation, so that's why we did this exercise yesterday. if you look at how rho transforms under general coordinate transformations, I mean small coordinate transformations, you find that it transforms like this. And this is psi 0, and psi 0 comes from, you remember, we have this coordinate shift. X mu goes to x mu plus psi mu. So this is the 0 component of the shift in the coordinate vector. In the coordinate. When we do a general coordinate transformation. So first of all, you see this choice was perfectly consistent during the initial phase, because there rho EDE was a constant, and then this term goes away. So this is a statement which is perfectly valid in any gauge. But once you have a fluid that evolves, saying that delta rho EDE is 0 is not a gauge invariant statement. So that already tells you that this is too naive. And then there's a second reason. It also ignores the physics of the transition. Because if you have a cosmological constant as a physical concept, then it just is going to be constant forever. I mean, it's a space-time constant. It's also constant in time. So if you want to have something to decay, you need some physical agent that makes that happen. So something has to happen. And now we are going to learn what that something can be, and I'm going to provide different examples. It can be a temperature, it can be another scalar field, but here we want a model-independent description of that. And what we do is, to describe that physical agent, we introduce a trigger. So introduce a trigger, which is a degree of freedom that kicks off this, this transition once a certain threshold value is reached. So think examples would be a dark sector temperature or another scalar field. So imagine there's a temperature in the dark sector, and once it reaches a threshold value, this happens. Or imagine there's a scalar field rolling in this sector, and suddenly it reaches a certain threshold value, then this decay happens. Okay, but here, so we are going to talk about models that implement these ideas more fundamentally. But here I want to stay model independent. So what I do, I introduce a transition surface. And I call that surface Q of, I think I use conformal coordinates, eta x. Okay, so it's a general function of time and space. And the picture is the following. And that's an important picture, so let's take some time in drawing it carefully. So there's going to be a threshold value. And once this Q reaches this threshold value Q star, the transition takes place. And in such a time-space diagram, this surface of could look like this. So this would be the surface where Q takes on this threshold value. And it doesn't have to be a perfectly constant surface. That's actually important. So we allow the Q to vary slightly. So the Q itself can have perturbations. That's at this level, Q is what you can think about as the trigger. And yeah. Yeah, you are going to understand better. So now in this picture, this transition surface defines the time when the transition happens. So before that surface, we have an equation of state of -1, and after that transition, we have this equation of state which is larger than a third. We have this decaying fluid. So before, after. And here we said the perturbations are 0. And here they are going to be non-zero. And there's the surface, and it's defined as this abstract function. Later we will identify that function either with a scalar field or a temperature. So exactly, yeah. It's a clock field. These concepts are borrowed from inflation. So in many regards, this is very similar to how you can think about inflation. In fact, this formalism of introducing a transition surface has first been done in the context of inflation. There's a nice work by Mukhanov and Deruel where they describe the transition from inflation as kind of this abrupt change in the equation of state. So this is the right intuition you have there. Okay, so this is a surface defined by the fact that this space-time dependent function takes on a certain value. So the value might be, so here in this region, Q might be smaller than Q star, and here Q is larger than Q star. And along this line, it takes this particular value. And I already, and that is then going to define an eta star of X. So the transition time becomes X dependent. Yeah. Before at background level, we just said the transition happens at a certain A star or eta star. And at background level, we didn't worry about space-time dependence, but at perturbation level, we introduce the space-time dependence. So that, as you see, is not constant. And this is eta star, okay, of X. So we introduce that. But now, how can we derive eta star of X? So the variation in the transition time or spatial dependence from Q, from this abstract trigger, okay? And so first of all, let me just summarize the transition defined as the condition that Q of eta star of X, so the transition time, which we call eta star of X, is defined as the condition that this function evaluated at eta star of X takes on this threshold value. Okay, this is a formal definition of eta star. It's an implicit equation for eta star of X. And we want to make it a little bit more explicit. So what we do, we do a variation of that equation. So let's vary this equation with respect to a change in, let's do a spatial variation of this equation. So you see there are two spatial dependencies via the time argument and via the space argument. So we have to apply the chain rule. So what we get is that we first, applying the chain rule, we first take the partial derivative with respect to eta. Star now always means evaluation at the background value of eta star. Times by d eta star, which is a function of X, the transition time, divided by dx. And then there's the second argument, and this is just the partial derivative of q with respect to dx. Also evaluated at that time, multiplied by the spatial variation. And this has to be 0 because the right-hand side is a constant. So if the variation hits the constant, it's 0. Okay, so how can we make progress with that? We need to do a decomposition into background and perturbations that you have seen now many times. So we can say q is a function of eta and x. So we can decompose it into a background q, which only depends on eta, which doesn't have any spatial dependence, and a perturbation, which depends on both. And we do the same for this transition time. But the transition time only depends on space. Well, it already gives the time itself as a value. So it has a constant background value. This is the eta star we worked with in the background description, plus a small perturbation. So we are looking at the case where these variations are small. This is the meaning of that. And so if this is kind of the mean value, this is really what we call delta eta star. These fluctuations around the background value eta star. Okay, so now I just plug in this decomposition into this equation. So what happens? Here you see that only the term survives where this is the background and this is the perturbation, because the spatial variation of the background part of the eta star perturbation vanishes. So what we get is, so I can pull out this spatial derivative. Let's pull it out. And what I get is q bar primed evaluated at eta star times by delta eta star. This is then just the perturbation. We work at linear order, so this is linear in the perturbations. Plus, okay, and here we just plug in this decomposition. The background value vanishes when I take the partial derivative with respect to space, and what survives is the delta q, and I pull out this spatial derivative. So what is left is just delta q star. So star always means evaluation at the background value of the transition time, so this eta star. And this is 0, okay? So now we suddenly have a relation between perturbations in what I call the abstract trigger and the time variations of when the transition happens, okay? So let me go all the way here. So this gives me an equation. I can solve that for delta eta star of x. Let's be careful with the arguments, which is minus delta q divided by evaluated at the transition time divided by q bar primed also evaluated at transition time. This is one important equation we need. And now, what we wanted to get is delta rho EDE, right? At this time, so the initial value. So how do we get from here to here? And now you might be reminded of what we did for the adiabatic initial conditions in the second lecture from inflation. There I told you that there's a notion of inflation ending earlier or later. It's different positions in space, and that gives time to these adiabatic perturbations. And something very similar is happening here too. Again, we have some transition which happens at different times at different places. So some places are ahead of time and some places are behind in time. So what you kind of a shortcut of deriving the perturbations that correspond to this time shift, what you do is you do a shift of the argument. And I can more intuitively explain in a second why this is the way to do it. Eta star prime minus delta eta, this shift we have derived here. So why am I doing it in that way? So the point is, you know, the background energy density is constant below the blue line, and it's decaying above the blue line. So now, if you are at this spot and you compare it with this spot, you see that here the fluid remains constant, the energy density up to that point, and then it decays. And here it stays constant up to this point and it decays. So here it decays later than it decays here. So it means that if you compare this point with this point, here the fluid already had more time to decay. So delta rho EDE is going to be negative here, and delta rho EDE is going to be positive here because it had less time to decay. Okay. Here it started earlier to decay from that constant value. Here it started later to decay. And and that gives rise to perturbations. And to derive them, you do exactly that. You take into account the shift in the decay time at different positions. So now I lost my notes for some reason. Just a second. Yeah, here we're back. So we Taylor expand that as usual, because these are small perturbations. And what we are left with is, so that is evaluated at eta star minus rho EDE bar prime, the background value at eta star, times by delta eta star. And this is our initial perturbation. So the final thing we write down is that delta rho EDE right after the transition is given by this expression. So it's minus rho bar primed EDE times by delta eta, and delta eta is this expression. So we get a plus sign, and delta Q over Q bar primed, and then everything evaluated at the initial time. And then we can use the energy conservation to rewrite prime in terms of the equation of state. That gives us another sign, and what we are left with is minus rho 1 plus W of this decaying fluid at the transition time times the Hubble parameter at that time times by perturbations in the trigger or clock field, if you think about it in that way. Okay. And this is, oh, and I need a factor of rho, the background rho. Okay. But I can take that to the other side and write it as a density contrast. Let's do that. And then we can delete it here. And this is our final matching equation. So this is how we choose the initial conditions for the perturbations in the decaying fluid. I should say this is kind of the intuitive derivation. There is also a more technical derivation which uses so-called Israel junction conditions. So whenever you have hypersurfaces in GR like this, there is a consistent way of connecting the metric before and after the transition, or something that is called the extrinsic curvature, and then you can go through that machinery and you will get the same answer. Okay. So how am I doing for time? Actually, not too bad. So now we have our perturbations after the transition. And I should say, I mean, you might wonder why all that worry about perturbations, but we are during the CMB epoch, and the CMB very much is an observable of perturbations. So changing the background expansion history without caring about observations is not, perturbations, sorry, is not going to work. So these are the initial conditions at this point, but now we need the dynamical equations that evolve the fluid further. And luckily, we have already derived the perturbed fluid equations before. I mean, today in the CMB lecture, you have seen an alternative derivation of the equation in case of dark matter perturbations. But we have looked at it for a general equation of state, and we derived this second order equation for the density contrast. But of course, we first need to make some assumptions. So closure of the perturbation equations requires us to know the equation of state. Well, that we already needed at background level, and there we said we take it to be a constant. But closure also now at perturbation level requires us to have an expression for the pressure perturbations. In the first lecture, we took the adiabatic condition, which simply says that these perturbations are related to the energy density perturbations via the adiabatic sound speed. So we are going to do the same here for simplicity mostly. But of course, these choices at the end of the day are going to depend on the concrete model you have. So what your trigger is physically. So right now, I just introduced that notion of this transition surface Q, but in a concrete model, this is going to be some degree of freedom, something, and ultimately these choices should be justified in a more microscopic theory. But here we want to remain model independent, and yeah, so we make that choice. And as you know, if W is constant, the sound speed is just W, so that is simple. And with these kind of simplest choices, we get that equation for perturbations. So there is a damping term, and there is a pressure term. And on the right-hand side, you can look it up in the first lecture, the expression. There is a source term that depends on the two gravitational potentials you have also seen this morning. But again, what is important from this equation is that it admits wave solutions. So there are going to be dark sector fluid waves in this decaying early dark energy fluid. It will correspond to it. On top of it, you will have perturbations. I mean, like dark sector acoustic oscillations, if you want to. So you can have sound waves in that fluid with a certain sound speed. Okay, and now let's get back to the initial worry we had already yesterday, and I think someone raised the question about it. So what is now going on in terms of the other parameters in the model, and how does it work out with the CMB fit? I mean, how can we actually see that this could give a sensible fit and isn't ruled out from the get-go? So let's look at phi, the gravitational potential, phi plus psi, the absolute value. You will probably learn tomorrow that this combination is what controls, for example, the integrated Sachs-Wolf effect. But for us, it's just a measure of the strength of the gravitational potential. And now, if you look at it as a function of time, as you have now heard many times, the gravitational potential is initially frozen. And then it, once the mode enters the horizon, so k equals the conformal Hubble parameter, which is a times h, then, and if this happens still during radiation domination, so let's say equality is here, then the mode starts to decay, right? And once we enter matter domination, we have solved that equation and seen that then a constant solution is the right solution for all modes, no matter whether they are super or sub-horizon. So this is the evolution of this. And imagine this is this lambda CDM evolution. So this is really the best fit lambda CDM evolution, what is required by the CMB fit. So now we have seen that these models require us to increase omega matter. So increasing omega matter means there's an earlier onset of matter domination. So so initially it's the same, then there's the decay, but this constant phase sets in earlier. So this happens if you increase omega matter. So now what happens if you turn on, this is without turning on this. This is what happens if you just take lambda CDM and crank up omega matter. So, but now you can ask what happens if you take lambda CDM and just crank up this FEDE. Well, that means matter, you add something to the fluid that behaves more like radiation, or even in a way it even has a bigger pressure than radiation, so it counteracts gravitational collapse even more. So this means in any case, that matter domination is delayed, happens later in this model. So what happens is that you enter this decaying phase during radiation. Once the mode enters, you're still in radiation domination, but now matter domination takes a longer time to set in, so you are going to get such a line. So this happens if FEDE goes up. And this is how you can qualitatively understand that these two things can balance each other. So this is the picture with perturbations, and how, I mean, initially people were quite surprised why in these models you can still get a decent fit to the CMB. And I think the first paper to really clearly point this out was one by Wen Hu and collaborators, which they called acoustic early dark energy, where they pointed out the importance of the decay of the gravitational potential and how it changes when you change these parameters. Okay. So, how am I doing for time? Okay. Yes, but this is everything at this stage I want to say about this effective fluid model. Now we have the background model, we have the perturbations, and then we are going, well, realistically, I wanted to talk in this lecture about hot NEDE. We called it like that because there we identify the trigger with the dark sector temperature, and it's really like that. We set them to be equal. So there is a dark sector temperature. It comes with its own adiabatic perturbations, and they define the perturbations in Q we looked at. But then there's also a model we call cold NEDE, because it doesn't have a temperature, so it's cold. And there we identify Q with a scalar field that drops out of slow roll. And this model has also been implemented in a Boltzmann code called trigger class. So it's an adaptation of the class code. So there's an exercise where you can play with that a little bit. But tomorrow I will, I think, only focus on this model as I'm running a little bit out of time. But in the notes, in the final notes, there will also be a section on this model. So you just understand it in this more general context. Yeah. Yeah. So very good. I mean, yeah, I'm going to talk about scalar fields now in the remainder of the time we have, but they are in a way very different, yeah, because here the trigger is a fluid, a temperature fluid, and it cools as space expands, and once it cools beyond a certain threshold value, this transition is triggered, and you can do it with a phase transition. And here the idea is you have an out of equilibrium situation. You have a scalar field that rolls down a potential, and once it rolls far enough, it triggers this transition also via a phase transition. So it's different ways of doing it, but both can be understood in this more general phenomenological framework I just presented. That's what I want to say here. Okay, but now let me do a little bit of homogeneous scalar fields, because this is what the AXI-EDE model is. It takes a more concrete approach. It uses a homogeneous scalar field with a non-trivial potential. So it's more like, a little bit more like inflation, where you also have a scalar field, and it initially slow rolls, but then it starts to oscillate around the minimum of the potential. So B4 is scalar field mechanisms. They give you another way of thinking about early dark energy. And scalar fields, I mean, they are also going to play a role for us in the case of cold NEDE, but here the idea is that it's the only thing you have. And scalar fields are important in cosmology. I mean, we have them in inflation, as you know, but also there are many models beyond lambda CDM, axion models, and so on that are based on scalar fields. So what I show you here is very generally applicable in cosmology and sort of important. So let's take the action of a scalar field, E for x minus g minus a half partial mu phi minus the potential of phi. So this is the action of a scalar field. And now imagine we have a potential which has a minimum. And then the scalar field initially sits somewhere in the potential, and eventually it rolls down and starts to oscillate around the minimum of the potential. That's the situation we are interested in. So I think in the inflation lecture, you must have looked at the equations of Klein-Gordon equations at some point. I'm pretty certain. So let me, if you haven't in detail, there's also going to be an exercise about that, if you have time for that. So the energy momentum tensor of such a scalar field is, I think I wrote down the expression before, minus 2 partial minus g Lagrangian over partial minus g. And then from this, you can derive the expressions for the energy density of that scalar field, which is going to be 1/2 in conformal time. There's a factor of 1 over a squared phi prime squared. That's the kinetic energy plus the potential energy. It's a homogeneous scalar field, so we assume it so there is no gradient energy. And there is also a pressure. And does anyone know how the pressure is different from the energy? Yes, just minus. Okay. So first of all, and this is the energy momentum tensor, and the dynamical equation is the Klein-Gordon equation, which would be that. And we can expand it for an FRW geometry. So what we get is this equation, phi double prime plus 2 times a conformal Hubble parameter. So if you do it in FRW time, there's a factor of 3 and the FRW, the standard Hubble parameter. But I like to do everything in conformal time. And minus a squared and the derivative of the potential. So that's the equation we need to solve. And since I'm running a little bit low on time, let me do it a little bit quicker. There is a more extensive discussion in the notes, but there are two regimes. There's regime 1, where the curvature dominates. So we can define an effective mass, which is 1 over phi times by the phi derivative of the potential. So if you have a quadratic potential, then this is just going to be the mass term. So if your potential is 1/2 m squared phi squared, and you plug it in here, this is just going to be the usual mass. So it's kind of a generalized mass for potential that could have a different shape. Okay. So then there's regime 1, where this effective mass is much smaller than the Hubble parameter squared. In that case, you see there is this damping term. This is an overdamped harmonic oscillator, so the field is stuck here and moves down here only very slowly. So yes, so in that case, one says the scalar field is frozen due to the Hubble friction. Okay, what does that mean for rho phi and the pressure? It means that these terms can be neglected because these are the kinetic energy, but if it's frozen, there is no kinetic energy. So what you get is that the pressure roughly equals minus the energy density. So what you see is that this field behaves like something with an equation of state of -1. So it has kind of a dark energy type behavior. But there is a second regime, the oscillatory regime, which is just the opposite one, when m effective squared is much larger than the expansion scale squared. And then you can what you get is a quickly oscillating solution. So the damping becomes subdominant and the field starts to oscillate quickly around the minimum of the potential. Okay, and so yeah, the corresponding equation is going to be phi double dot equals, so we just drop this term minus a squared. Okay, that's the equation in the second regime. And what we can do now is calculate, and that's we can calculate in that case the equation of state for general potential. So what we get is, so let me write it down again, phi double dot is minus a squared d phi, and we get fast oscillations with period capital T, and capital T is much smaller than the Hubble time at that time. That's the statement that these oscillations are fast. They are fast compared to the expansion of space. So within one oscillation, we can assume that the scale factor is constant because it happens so quickly. Space isn't expanding really during that time. So what we now do, we cycle average So we take our expression for the energy density and we average it over one cycle. So let me be explicit. We integrate from eta to eta plus t. T is the period, and we divide by the period. And plug in the expression for the kinetic and the potential energy. Okay. So now we can use the equation of motion, this one. So what we do is, let's write it in that way. We have phi prime squared, so we can integrate by parts. So this derivative hops over to that, so we get a second derivative. Note that we assume that A is constant within this time interval. So we can just ignore when the derivative acts on A. And then we get the second derivative, and we can use that equation to eliminate the second derivative. That's what we are going to do. And what you end up with is this, eta plus t, d eta, 1/2 phi. The a squared goes away. dv d phi plus v of phi. Okay, and now we do an important trick. We write that as one derivative. So we can say this is the same as 1 over phi times by partial phi acting on phi squared v of phi. Okay, so you see, if you take that derivative, the first term is going to give you, then it acts on this guy, so it gives you a factor of 2. So probably I need a factor of 2 here, yes. And then the remaining phi cancels this one, and we are just left with v. So this is going to be this term. And when the derivative acts on this guy, we are left with exactly this term. Okay. Very nice. And now we can do the same for the pressure. So that was the energy density. Let's do the pressure now. And it's the same steps, but the final answer, just because there is a sign difference, it's easy to work out for yourself. The final answer is going to be an eta integral, but now it's not 1 over phi, it's phi cubed. d phi, and I think phi to the power minus 2 times by v of phi. So now we have two expressions, one for the energy density, one for the pressure, in terms of the potential, and an integral over the potential, these two expressions. And now what I want to do is assume a monomial potential. So what is a monomial potential? It's one which is just a power law. So v of phi is proportional to phi to the power 2n, so that's for convention. So n equal 1 would be just a standard massive scalar field. N equal 2 would be some higher order self-interacting theory. And if we just plug that into these expressions, what we find is that rho phi, so what we do, we plug it into this expression. Now we multiply phi squared with that. That gives us 2n plus 2. We take the phi derivative. This brings down 2n plus 2. So what we get is a factor of 2n plus 2 divided by 2 times the, and what remains is just the d eta integral with these boundaries of v of phi. So yes, so if you see that you have phi to the power 2n plus 2, taking that derivative makes it phi to the power 2n plus 1, and dividing by phi makes it phi to the power 2n, which gives back the potential. Oh, they are non-renormalizable potentials if you go to n larger than 2. Yeah, n larger than 2. Up to 2, it's still fine. N equals 2. Yeah, well, it's not per se problematic to have non-renormalizable potentials. Then you just have to be careful about quantum corrections and how you organize your low energy description. So you can go higher, but then you have to be aware of what you are doing. Yeah, and okay. You do the same for the pressure, and what you find is that you get 2n minus 2 over 2 times the period. Okay, and now we do what we do all the time in this lecture. We take the ratio of the pressure and the energy density and say this is what we call the equation of state parameter. I mean, in this case, it's really an effective equation of state parameter, which only holds if you coarse grain over small time intervals. But what you see is we get 2n minus 2 divided by 2n plus 2. So in other words, n minus 1 divided by n plus 1. And that is quite interesting, right? Because let's look at a few cases. N equals 1, it's a quadratic potential, so only a free scalar field with a mass. And what you find is that the equation of state in that case is 0. So this is interesting. So you can have a scalar field that behaves like dark matter just by oscillating around the minimum of the potential. This is a non-equilibrium situation. There is no fluid. There is no Bose-Einstein distribution of particles or whatever at any point. I mean, it's an out of equilibrium situation. And this is, for example, what people have in mind when they talk about axion dark matter. Okay, so this is why I said, I mean, having homogeneous scalar fields is a rather generic concept in cosmology. So let's look at n equal 2. Then it's phi to the 4, still renormalizable. So I think you will still be happy with that. Then 2 minus 1 divided by, so we get a third. So we have something that looks like radiation, even though it doesn't have to do anything with radiation microscopically. But now let's look at n equals 3. We get phi to the 6 and an equation of state of 1/2. And here, indeed, you have to worry about the fact that it's a non-renormalizable theory. And yeah, but this is this is really what kind of, let's call them thawing dark energy models. Thawing early dark energy models exploit. So as I argued before, in these early dark energy models, you need a very quick decay of this early dark energy fluid. So 1/3 wouldn't quite make it. I mean, would still maybe give a somewhat interesting fit, but what you need is a quicker decay. So when people look at early dark energy scalar field models, they often look at scalar fields that oscillate around the minimum of the potential with a potential that goes like phi to the 6 close to the minimum. So this is also what ICTS-TIFR is doing. This is how you realize the quick decay in these models. So let's, in the last 5 minutes, let's look at the ICTS-TIFR model because it's a little bit more complicated than just a monomial potential. You can study, by the way, by just taking this model seriously, say this is your fundamental model, and saying this is your EDE, you get this rock and roll EDE model. I don't know if you've heard about it. I guess rock and roll because it rolls or whatever. But But that turns out to give not a particularly good fit to data. But it was one of the earliest models shortly after the AXI-ED model came out. And this, of course, simple. So let's talk about AXI-ED. So as I said, monomial potentials do not work well. So potentials like that. What works better is a potential like this, and this is the potential the AXI-ED model looks at. So you have some coefficient that depends on n times by 1 minus cosine phi divided by f to the power n. You can get those potentials from axions in principle. I'm not going to have time to explain much about axions, but what is important is that axions have theories which have a shift symmetry, which is broken down to a discrete shift symmetry once you include non-perturbative corrections. But the bottom line is you get potentials of that form which have a discrete shift symmetry. So the shift symmetry in that case would be phi goes to phi plus 2 pi f. So this theory is invariant under such a shift. And that, getting back to your question about renormalizability and so on, I mean, this symmetry, you have a symmetry principle in this theory that protects you and allows you to do these things. But the problem here is that you normally have a sum over all of these n's. So you could have different powers. But what AXI-EDE does, AXI-EDE looks at only one power. It says n equals 3. And then what you find is a potential that looks like that. So you only consider a field range where phi goes up to 2 pi f, and then you have something that looks like that. So it compared to the monomial potential, it flattens at higher field values. And it turns out that this flattening is important for perturbation theory to work out, because in these theories you have interactions, and the sound speed is kind of depends on the initial field value, and the perturbation theory, as you know, depends on the sound speed. So having such a potential or such a potential makes a difference at perturbation level, not so much at background level. There, the phenomenology is very similar. So how do we understand now how we get what's going on? So initially the field is frozen. It sits somewhere here. And again, it's frozen due to Hubble friction. So there's the effective mass scale would be much smaller than the Hubble parameter squared. But then at some point, Hubble drops, right? And the inverse is true. So the effective mass scale is much bigger than Hubble. And then the field starts oscillating around the minimum of the potential. It's again a damped oscillation, so we are quickly down close to the minimum. And then we can expand this here for n equals 3. So let's expand it. That's simple. So we get so the cosine. Let's expand the cosine first. It gives us the leading term would be 1. And then we get 1 minus, but with that minus, we get a plus phi squared over f squared, right, to the power n. So these cancel. So what we get at the end is phi to the power 2n, but n is 3 now, so phi to the power 6 divided by f to the power 6. Did I do it right? I think so. Yes. So what you see is indeed that we are in a situation close to the minimum. It's described by, it's the same situation as the one we studied before. And we get an equation of state, which is a half, so larger than a third. So in this model, let me clean this up a little bit. So yeah, I'm close to finishing. So in this model, you have the first phase where the field is frozen, where W, it's not perfectly -1. That's a slight difference to the phenomenological model I presented before, where W is early dark energy is close to -1 because it's still slowly doing a slow roll. But then there's the second phase where W EDE is 1/2, where the field starts to oscillate. And so this is an alternative approach to early dark energy. And you could say it has many similarities with the phenomenological approach I presented to you, but it's also distinct because there's not this trigger element, and also the transition from slow roll to this quick oscillations is relatively slow. So it takes several Hubble times to go from one regime to the other. So it's not an abrupt transition. So the models I'm going to talk about tomorrow, these phase transition models, they achieve something that happens very quickly on cosmological scales. Whereas this is here you have something that first starts to oscillate relatively slowly. So this approximation is not yet applicable, and only later on you end up with that regime. But nevertheless, this is one of the phenomenologically at least promising model. But there is a problem, and I mean, which is this choice of n equals 3, because what you need to do, you need to set the lower order terms to 0, so, or close to 0. So you need that V1 and V2 are close to 0, and this is a fine tuning. So there you have to worry about whether you can write down a fundamental model that gives you that. So that's a theoretical challenge these models have. But nevertheless, from a more phenomenological perspective, these models do pretty well in terms of data fits. So they, with standard data sets like standard BAO and Planck 2018 and Pantheon supernovae data, they bring the tension down to around 2 sigma, from 5 to 2 sigma. This is why people got excited about this class of models, and which is maybe a good point to stop. And tomorrow I'm going to talk about a different concrete model that doesn't have that problem, but provides a different type of physics to realize a quick transition from this -1 to the decaying fluid, more in line with the phenomenological description I presented in the first part today. Thank you. Mm. No, with inflection points. No, I mean, there are similarities with inflation, but there are also huge differences to inflation. So what is very important is, in all this, we are still in radiation domination. The energy corresponding to this field makes up maybe 10% of the energy budget. So we are never at any point in a de Sitter or quasi-de Sitter. So this is an important distinction. So in terms of the field mechanics, how the equations look and how you you work with them, it's very similar, but physically it's in a way also very different. Yeah. You're never, for that you need a de Sitter or quasi-de Sitter. We are always doing radiation domination. Modes are never going to leave the horizon. That's important. And also in inflation, here, what I mentioned as one of the problem with this AXI-EDE is we need a very particular minimum of the potential, which is not quadratic. But this is a very non-generic choice. Because in physics, we like the harmonic oscillator, right? This is our main paradigm, if you want to, which would correspond to a quadratic minimum. I mean, this is what we expect a minimum to be. But here we need a minimum that is much more shallow, 5⁶. And in inflation, if you think about standard inflation with reheating, we still would have a standard phi² potential. So this is very unique to this class of models. Yeah, maybe the other question, if that's all right, so yeah. Yeah, so, I mean, let's talk about the phase transition model tomorrow, right? This is just going to be a way of explaining why the equation of state suddenly goes from -1 to something else. But you're asking why do you need a shallow potential here and not a quadratic potential? Well, imagine you take a quadratic potential at the minimum, then you get an equation of state of 0, right? And that means that early dark energy is quickly going to dominate the energy budget because it happens during radiation domination. You have something with an equation of state of 0 that behaves like matter. It decays less fast than radiation. So it's not a localized energy injection anymore. So you suddenly produce a lot of, in other words, you suddenly produce a lot of dark matter. So then your early dark energy decays into something that behaves like dark matter. And that's simply not possible phenomenologically to create such a huge amount of dark matter at this relatively late time. Yeah. So you need something that is more, the rule of the game is you want to shorten the sound horizon, but you want to do it in a way which minimally affects the lambda CDM cosmology. So you want to have kind of this peaked energy injection that comes and goes quickly. But for that, you need a shallow potential here because only that gives you a large equation of state and a quick decay. Otherwise, the decay is too slow. Yeah. So, suppose the desired equation of state is yeah. You want it to behave like matter. Okay. Yeah. So can a non-monodal potential work? Yeah. Because lambda phi terms as well. You still get omega W equals 0. Phi. So you want to have phi to the power 4? No, so I want phi² plus phi. Yeah. Then it's that's fine. I mean, phi² plus phi to the power 4. So you put a mass scale here. Then for large field excursions, you feel this power, so it behaves more like radiation. And as the amplitude drops of the field, you start exploring more this term. This becomes less important, and it transitions to something that behaves like that. Yeah. That's right. Mm-hmm. I think you had another one.
So we saw that the sound speed, is for the fluids that have some perturbations. Yeah. So when W equals to -1, there is no perturbation. Yeah. Sound speed in cosmological constant does not move anything. No. But there can be other fluids that has equation of state from -1/3 to -1. Yeah. So what does sound speed mean for them? Because then that they will have delta Q and delta P of physics science.
Yeah. Well, you just look at the, I don't know if it's still there, no, probably not. You look at the second order equation for the density perturbations, what we call delta. And you find that in some cases, not all of them, now I'm not entirely sure about this threshold, if it's minus the third, I think it has to be larger than 0, the equation of state, for this to be an oscillator equation. But then you can ask, take that equation and just solve it, and you get wave solutions, and from these wave solutions you can read off the propagation speed, and that's what, and you will find this is the sound speed. But in some cases, this is exactly not what is happening. For dark matter, you don't get oscillatory solutions, you get growing solutions. So then there is no notion of a sound speed. I mean, you can formally write it down and say the sound speed is 0, but what does that mean? Yeah. Yeah. Okay, thank you.